The next section, 4.6, is on bond dissociation enthalpies. Oh no, enthalpies. Coming back to haunt us from general chemistry. I promise you that this will not be anywhere near as bad as it was in general chemistry. And by bad, I mean good. So let's go back to the chlorination of methane, the looking only at the formation of the monochlorinated product, chloromethane. Looking at just this one particular aspect of the reaction. Let's say that we wanted to understand the mechanism of just this reaction, not of the dichloro or the trichloro or the tetrachloro products, but just this one here. If we wanted to understand the mechanism of this reaction, that means that we want to understand exactly how this product is formed from these reactants. We want to know exactly which bonds are broken and exactly which bonds are formed and in what exact order. You know, we have all these possible propagation steps and all these possible termination steps, and we want to know exactly how it goes down in the formation, in the process of the reaction. And we can see by looking at this that we are going to break a carbon-hydrogen bond, and we're going to break a chlorine-chlorine bond, and we're going to form a chlorine-carbon bond, and we're going to form a hydrogen-chlorine bond. But the question is, in what order does that all happen? What bond breaks first? Is another bond broken before one of the other bonds is formed? Which bond is formed first of the two? The way that we can figure this out is by calculating the enthalpy of the reaction. Now, we're not going to calculate the enthalpy of the reaction in the exact same way that we did in Gen Chem, which was just products minus reactants, because if we do that for this reaction, we're going to get the same enthalpy regardless. The way that you learned it in Gen Chem, it just looks at the total enthalpy for the whole entire reaction, which is going to end up, because of Hess's law, it's going to end up exactly the same no matter what order the bonds are made or in what order the bonds are formed. So we're going to look at the enthalpy of the reaction in terms of the bond dissociation energies. And we're going to say that the enthalpy of the reaction is the sum of the bond dissociation enthalpies of all of the bonds that are broken minus the sum of the bond dissociation enthalpy, that's a D, for all the bonds that are formed. Now I know you're so used to products minus reactants from Gen Chem. We're not using that here. The way that I remember it, the way that this sticks in my head, is that it goes in alphabetical order. It's the B minus the F, the broken minus the formed. The bond dissociation enthalpy, just so that I want to make sure that you really know what we're talking about here, is the enthalpy required to break a bond homolytically. Homolytic cleavage. The word homolytically might be new to you, but for as much as you've learned science, you can figure out what it means. You know already that homo means the same, and lytic, lysis, you know from biology, means to break or to burst. So a homolytic bond cleavage is when you're breaking a bond in the same way. That means that in this particular example of a reaction, the chlorine-chlorine bond in the Cl2 molecule, when it's broken homolytically, both of the atoms in the bond get the same electrons coming out the other end of the reaction. One electron goes to one atom, the other electron goes to the other atom. In contrast to that, just to make sure that you understand it, the other possibility, which we don't see in the free radical mechanism, but we do see in other situations, if both of the electrons were to go to one of the atom in the bond, there we have a heterolytic cleavage, where the two atoms on the other end, they don't come out the same way. So, like I said, if we were just to simply calculate the enthalpy of this reaction, the bonds that are broken, which is the carbon-hydrogen bond and the chlorine-chlorine bond, minus the energy of the bonds that are formed, the carbon-chlorine bond and the hydrogen-chlorine bond, we're going to come up with the same number no matter what the mechanism is of the reaction, no matter in what order the steps actually occur. So in order for us to figure out how the reaction actually goes down, we have to propose a bunch of different ideas, a bunch of different possibilities. And those are all going to be tentative mechanisms for the reaction. One mechanism, one possible mechanism, which we're going to go ahead and just call mechanism number 1, would be like this. And nobody's disputing the initiation, the cleavage of the chlorine, this initiation step. That's how the reaction starts. There isn't another initiation step, so this has got to be it. The dispute comes at the propagation part. We're not really sure what that chlorine radical does. So one possibility is we could take the chlorine radical and react it with a molecule of methane and end up with chloromethane and a hydrogen radical. This equation's got to be balanced in terms of the atoms, so we've got to have the 2 chlorines, the 1 carbon, and 4 hydrogens coming out the other end. And then that hydrogen atom, or hydrogen radical, goes on to react with another molecule of chlorine, Cl2, to make the HCl product that we do observe, and a new chlorine radical, which then goes on to do who knows what. We're just going to look at those 2 steps. Another possible mechanism would be if our chlorine radical, reacting with the methane molecule, first produced the methyl radical and HCl. And the methyl radical reacted with another molecule of chlorine, Cl2, to produce the monochlorinated product and another chlorine radical. If you add these reactions up, the way that you learn to add up reactions in Gen Chem, summing them up, Hess's law, you're going to see that they are both going to add up to this overall reaction here. And they have to, because otherwise it wouldn't make any sense. But if we look at just, canceling out the chlorines, I'm not actually going to cross them off like we would do in Gen Chem because we don't want to do that here. But we do have, we'd cross off the chlorines, we'd cross off the hydrogen radicals, we'd have a methane and a Cl2 reactant, and chloromethane and HCl as our products. And then in this reaction down here, we're going to have the same thing. The chlorine radicals are going to cancel each other out. These methyl radicals will cancel each other out. And our reactants will be methane and chlorine. Our products will be HCl and chloromethane. So we're going to add up to the same overall reaction. And that means that the overall delta H for mechanism 1 and mechanism 2 are going to be identical because they're the same overall reaction. But if we look at the delta H's for the individual steps within the mechanism, step 1 of this mechanism, in this reaction, we're breaking a carbon-hydrogen bond and we are making a carbon-chlorine bond. In step 1 of mechanism 2, we're breaking a carbon-hydrogen bond, but we're making a hydrogen-chlorine bond. So these 2 step 1s are different. They're going to have different enthalpies. And the 2 step 2s are also different. We're breaking a chlorine bond in both of them, but here we make a hydrogen-chlorine bond, and here we make a carbon-chlorine bond. So we're going to have a different delta H for the individual steps.